Oop. And now I got to share my screen. Which one is it? This one. Everyone see the question?
Yes.
Yeah.
And everyone read the question. The picture is a bit, yeah. The third one's a little difficult to read. It's because of my monitor's refresh rate and the fact that I zoomed in on it. You can see the pixels. All right. Also, that mouse that you see is not my mouse, by the way. That's part of the picture. All right. So question one. Question one is homework 1/2 topics. In my opinion, pretty straightforward stuff. So we can go through this really quickly, I assume, unless there's questions. So we start with A. Well, we'll read the question out. I'll just start. Consider a silicon crystal at room temperature under equilibrium condition and doped with donor atoms of density Nd is equal to 10 to the 18th. So this is an N-type silicon crystal. And then you assume the silicon crystal has an electron and hole mobility given as, mu n equals mu p is 100 centimeters squared per volt seconds at, room temperature. So there's that. So the first thing it asks is to calculate the free electron and hole density. So first off, we know that this is majority electron. So when it asks for the free electrons, N0 directly is equal to Nd, which is directly equal to 10 to the 18th. So that's all you need to do for the electrons. And then for the holes, we have to whip out the law of mass action, which happens to be N0 times P0 is equal to Ni squared. Rearrange that to solve for P0, and you will have N0 over, no, you will have Ni squared over N0. You'll have Ni squared over N0, which is 10 to the 20th over 10 to the 18th, which yields 10 to the 2nd or 100 holes for your concentration for your P0. So P0 is equal to 100. Any issues with the law of mass action? Take that as a no. Don't think so. It's not that bad of an equation. It's pretty basic. It's just you got to know when to use it. If this were, let's say real quick, I'm going to give a test condition because there's a chance this would happen on the test or the midterm. If Nd was equal to, let's say, 10 to the 11th, there would be a different formula we would use. We wouldn't use the law of mass action anymore, I believe. I'm pretty sure when they start, because the law of mass action is only viable if there's a difference in the order of magnitude of the holes and electrons of greater than 10 to the 3rd, or greater than equal to 10 to the 3rd. So if you're at 10 to the 11th, that's a problem because it's not possible for the amount of holes to be, greater than, like the difference in the amount of holes to be greater than 10 to the 3rd. So instead you use a different formula, which is like the quadratic solve formula he showed us like once a while ago, and we had to use in our, I think, our first homework. So that'll be put on the, we'll talk about that later when we're setting up the formula sheet, but just know that that might be, like this question's really easy unless it gives us a trick question like that where we have to change up our formula. All right, then we go to B, which is draw the energy band diagram showing the relative position of conduction and valence band and Fermi energy. So this is a draw plus a thing. So since we are actually submitting files this time and it's not multiple choice, well, I think it is actually, I think he said that we submit a file, but it's also multiple choice or something, if I remember correctly. Either way. So there's a formula for this as well as a component where we'll actually be scored on, our proper drawing of the energy band diagram. So the actual formula for this to start is just EF minus EI is equal to KT over Q, which is a quantity number we have. So we can KT over Q times ln, and it is what it's isn't it Ni over? Let's check the formula sheet. It's yeah, Ni is in the denominator, and then it's divided by the majority carrier here. So we would do Nd divided by Ni inside of the ln. And the KT over Q is a known quantity. So normally when I write this equation, I literally just do 0.026 times ln of your inside stuff. So to find the Fermi energy of like a question 1 type question, because we've gotten used to doing like homework 3, where we're solving for what are they called, pseudo Fermi levels or whatever, quasi Fermi levels, where there are 2 of them and they're split because at the end of the day, since there's actually like, you know, the majority carrier concentration stays unchanged in the MCDE questions, but the minority concentration carrier, like the minority carrier concentration changes and actually goes up to comparable and or greater levels than the majority carrier. Therefore, there are two separate Fermi levels. But now that we're going backwards, we no longer have to solve for two Fermi levels, because the majority carrier is so much larger than the minority carrier that the minority carrier's Fermi level is essentially indistinguishable from EI. So it doesn't need to exist. So in these questions, in homework 1-2 / questions or question 1 type questions, you only need to solve using the majority carrier density, which is given to us as 10 to the 18th here. So the solve here is 0.026. That's our quantity that we, it's just a constant for all of these questions, times ln of 10 to the 18th divided by 10 to the 10th, because it's just ni, not ni squared here. So that's just, obviously that's just ln of ln of 10 to the 8th. ln of 10 to the 8th times 0.026 will give you 0.478 electron volts. And since this is a majority carrier of electrons, that Fermi level is squarely above EI. So it's actually plus as opposed to minus. If we were working with holes here, that Fermi level would be squarely below it because the holes are the majority. So it's important to remember where to, because obviously now we're being scored on our actual, you know, graphs and drawings. So it's important to know how to draw the like the basic Fermi level graph or figure. Does anyone have any trouble with drawing those or like understanding how to draw them?
I honestly am just copying down whatever's on the slides every time. Is there a different way to do it, or is it just the same thing?
So for question like 1, question 2, the Fermi level, like basic Fermi level structure of the figure is the same. It's just your Fermi levels, that being like your dashed lines, have different positions based off of your solution. For homework 1-2 style questions like this one, your Fermi level is one dashed line, and it's either above or below, depending on what your majority carrier is. And the figure remains the same. Nothing changes with the figure. When you go to MCDE questions, there are two Fermi levels, but the main figure is still the same. It's just that one Fermi level is above, one Fermi level is below. And then we get to question 3 questions, homework 4 style, with the Pn junction, where the overall structure of the Fermi level figure itself is fundamentally changed. It's completely different. It looks more like, let's see. Oh, I have so many of these open. So here's like the standard Fermi level we're used to, this one. This is also weird stuff. Does he have it? He might have it right here. No, this is just him going through like a million different things. All right. Then we will close that real quick and go to his Pn junction. This should give it to us. So for Pn junctions, it's this. This is what it looks like. This is what the Fermi level thing looks like. He added a bunch of extra stuff here. Let's see if there's a better drawing of it where he doesn't have all the, yeah, here it is. Here's what it should really look like. So you'll have, and this is Pn junction. So remember, you got to make sure that your P's over here and this over here. And it's literally solid squiggly, solid squiggly. This EI remains at the center. This stays. Wait, no, yeah, this is EI. And then the trick is EF is different. EF is follows the shape of the like solid lines, but it's a dotted line. It would start like at the, can you see my cursor? Are you guys able to see? Yeah, it would start as a dotted line here, go dot, 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 dot. It moves. Like at like the 0 position, the Fermi level is equal to EI, and then it goes back. So it's a squiggly. So we can talk about more of that later when we reach the Pn junction question. So let's open back up the proper photo. This one. I gotta zoom into it again. Oh boy. I want to zoom into it again. Okay, wait, what's happening? There we go. All right. So that was B. Can't zoom into it right now. This screen sharing thing prevents me from reaching it. So hopefully you guys can read it well enough. All right, so now that's part B. So that's just how to calculate like the original Fermi level. That one's pretty plug and chug. It's more difficult to understand how to draw it than it is to calculate it necessarily. Then we're on to C, which is calculate the resistivity. So this changes it up a bit. Resistivity is its own function, its own formula. So if I remember correctly, I have it in my notes, but does anyone remember the resistivity equation off their head? I remember it was back near the beginning. It was a homework 2 topic. Yeah, here it is. Found it. All right. So the resistivity equation for homework 1-2 style questions is rho is equal to 1 over, and I like to draw this a little bit in a simpler way. So if we look here, there's 2 pieces of information we need to know when using the resistivity equation that can actually simplify our work and make it a bit faster. First things first, in the equation, Q is written for both terms in the denominator. We don't need to do that. We can instead write it as a distribution over a parenthesis. So there's a Q. And then the next thing we need to know is, looking at this question, it notes that the mu n and the mu p value are equal to each other, and that value is 100. So that means you can pull that out of the equation as well. So you have Q times, your mu. So this is just Q times 100 here. And then that would be times your ND plus your P. Yeah, that would be the ND plus your P. So it changes up a bit. So ND plus your P value. So this would end up being, our equation would be 1 over Q times 100 times the quantity of 10 to the 18th plus 10 to the 2nd. So the trick here is, since this is a single majority carrier question, 10 to the 2nd is so many magnitudes smaller than 10 to the 18th that you can simplify that whole quantity to simply just be 10 to the 18th, because 10 to the 18th plus 10 to the 2nd is just 10 to the 18th. It doesn't make a difference. So you can do 1 over, so the value I use for Q is 1.602 times 10 to the negative 19th. But most people just do 1.6. So then you do that. So 1.6 times 10 to the 19th times 100 times 10 to the 18th will yield us our resistivity. So the first thing that you can note is that this resistivity should be relatively small. When we're working with a doped silicon with majority carriers, its resistivity should be quite small. If it's intrinsic silicon, it should be pretty damn high. So we can confirm this right now. We can do 1.6 times 10 to the negative 19th times 100 times 10 to the 18th. That gives us 16, it looks like. Let me do 1 divided by 16. 1 divided by 16 is equal to 0.0625 ohms. So it should be pretty similar to that, pretty confidently. So for most questions like this, your resistivity, if asked to calculate it, and if asked to calculate it at a place, because there's a chance that it might vary with position in later questions and change up the resistance value. But in this case, the resistivity should straight up just end up being very, very low, like less than 1 ohms level low, because just standard doped silicon has a very, very low resistivity. Because at the time when it's doped, it ends up being a conductor, like a really, really good conductor. So does anyone have any trouble with that formula? That one's really plug and chug. So we'll just we'll get the formulas. You can simplify it into several versions of the parent formula, and we'll put those on the formula sheet later. So are there any questions about that besides that part? No. All right. Cool. Next. Yet again, it asks you to compute the resistivity, but instead it says compute the resistivity of an intrinsic silicon crystal. So what does that mean?
No. I mean that they win. You were in here when they lost.
Huh?
You were in here when they lost.
I wasn't in here when they lost the losers bracket. I was in here when they lost the regular one.
No,
Someone lost, I guess.
Someone took the
Dr.
L.
Disrespect, rest in peace.
Did Dr. Disrespect lost?
Yeah, dude. Losers bracket.
What did he lose?
Warzone tournament.
Oh, get wrecked.
I know, bro. Sad days for the
I was
dog.
in here when they were down 12 kills.
That's no fun. All right, so for intrinsic silicon, I'm pretty sure the intrinsic silicon resistivity is constant, if I remember correctly, and it's a pretty high number. somewhat interrupted. So the intrinsic silicon resistivity is essentially constant. And oh yeah, wait, no, I gotta correct something real quick. This might lose you some points if you were to make this mistake, like I almost just let it happen. The unit on resistivity is ohm centimeters. So make sure you write ohm centimeters and not just ohms, like electrical engineers tend to do when they think of resistance. Because resistivity is fundamentally different than resistance, because resistivity is actually a component of the greater resistance formula, so it's different. All right, so there's that. So now the resistivity of an intrinsic silicon crystal, how does it compare with doped silicon? So first off, the resistivity of intrinsic silicon is absurdly large compared to doped silicon. And second off, computing it is possible, but I'm pretty sure he just gave it as a constant value, because since it's resistivity is, for all intents and purposes in this case, it can be, for an intrinsic silicon crystal, it can be material dependent, assuming no temperature change. So I think it was like 625 mega ohms or something ridiculous like that. I can actually check this. Because remember, Ni is the intrinsic silicon level. So your formula would now just be rho is equal to 1 over Q times 100. Yeah, times 10 to the 10th here. So what does this do? You do 1.6 times 10 to the negative 19th times 100 times 10 to the 10th power. And you get 1.6 times 10 to the negative 7th or something. You take that, divide 1 by that, and then you get, yeah, it's the exact number I just said. So it is 1, 2, 3, 4, 5, 6. 6.25 mega ohms per centimeter. So for calculating this, Ni is just the intrinsic silicon carrier density. So you just take that and plug it in instead, and you'll get the number that we got, obviously, the 6.25 mega ohms per centimeter. So that is a constant value for intrinsic silicon. That doesn't change. So on your formula sheet, you can do one of two things. You can either write down the formula for intrinsic silicon and just replace the Nd or the P with Ni, or you can just write like rho, like intrinsic is equal to like 6.25 mega ohms per centimeter. Either way, because that's essentially a constant and that won't change.
Oh, it's always that?
Yeah, because intrinsic silicon is obviously undoped. There's nothing that changes about it. That's a materially dependent parameter. So
Right.
the only thing that could possibly change it is if the silicon crystal was at a different temperature. But since this question said room temperature, a silicon crystal at room temperature has a constant resistivity value of 6.25 mega ohms per centimeter. That won't change. So you could just write that down on your formula sheet if you wanted to. Yeah, or you can remember it either way. And then the last part of this question is E, which is how the resistivity of intrinsic silicon and doped silicon changes with temperature. Now this, you see, like this, that is the exact thing I was just talking about. So he has this. So the resistivity of intrinsic silicon drops, just hits the ground when it comes to increased temperature, because it starts super, super high. But when you increase the temperature of an intrinsic silicon crystal, you increase the amount of kinetic energy in the lattice, which allows more electrons in the holes to be more electrons to be freed, thereby creating some parent like positive ions and everything. So you create more carriers by heating it. And since you created more carriers, that actually causes the resistivity to go down for the intrinsic silicon crystal. So the graph of resistivity versus temperature for an intrinsic silicon crystal starts at a really high number near like 300 or whatever, or like lower. And then as the temperature increases, it very, very quickly drops and steadily approaches like the x-axis or the temperature axis. Now, the graph looks slightly different for a doped piece of silicon. The start is the same. It starts really, really high because at low temperatures, you reach the freeze out range where no carriers are produced regardless of doping. And then once you reach, like a higher than that room temperature range kind of stuff, you get into what's called the extrinsic zone, which actually causes resistivity to go up slightly. Because remember, since we already have a high amount of carriers in a doped piece of silicon, until the heating releases enough intrinsic carriers to be actually like, within like a certain order of magnitude of the amount of carriers already present, you're not making new carriers. So increasing the heat will only cause the resistivity to increase as opposed to decrease for a short period. But once you heat it up to a point where intrinsic carriers can catch up to the amount of extrinsic or the amount of doped carriers present, then the resistivity will go back down once you reach a sufficiently high enough temperature. And then it'll go back down and go back to the intrinsic zone. So for that, obviously, I don't know if you can put that on a formula sheet, but that's something that was in the notes. Like I'm looking at my notes right now to remember what these things look like. And that's just like a piece of theory that you're gonna have to memorize essentially for that part, just that graph part. I guarantee it's gonna have us do this, like the graphing and the resistivity stuff, because with regards to question one is obviously addressing homework 1 through 2. So because of that, it's got to cover both like regular law of mass action, like charge neutrality rules, and then it's got to also cover, resistivity and resistivity change via temperature. So those are the 2 topics that you should expect covered through question 1s that we'll see, assuming that like he keeps the midterm in the same order, like question 1's like homework 1 through 2, question 2's like homework 3, question 3 is homework 4, that kind of thing. That we're assuming that, and hopefully he does. That would make the most sense at least. So that's the full question 1. Are there any questions on anything part of question 1?
Just to recap, so for the graphing, basically it just decreases as temperature goes up.
Yeah. So for part E, for intrinsic silicon, it strictly decreases, and there's a shape to that graph you're going to want to remember. It starts really, really high, jumps, like goes down really, really quickly, and then like curves off to be like almost parallel with the x-axis. Because obviously the resistivity won't be 0 because that's bad. It'll be just really close to 0. And then for your doped, and this is for N type or P type, doesn't matter as long as it's doped. It also has the same starting characteristic because regardless intrinsic or doped, it'll still be in the freeze out zone where the temperature is so low no carriers can be produced regardless of doping. Once it gets past that, for a doped piece of silicon, it gets into the extrinsic zone, which causes the amount of carriers to, not increase for a strict period of temperature, simply because the amount of intrinsic carriers being added by the breaking of bonds through the intrinsic silicon that's still present isn't significant to the overall amount of carriers already present from the doping. And because of that, the resistivity goes up for a short period of time. And then once you get past the extrinsic zone and the amount of intrinsic carriers being generated by heat like catches up to the amount of doped carriers already present, the resistivity will drop back down and fall in line with what you'd expect to see in terms of resistivity levels at the intrinsic silicon. So I will.
That one would kind of look like a sine graph at first.
Kind of, yeah. So it starts really, really high, drops down, has a little bump that goes up, and then it drops down again towards the x-axis. So that's what that looks like. And then the other one starts really, really high, drops really, really quickly, slopes off to be parallel to the x-axis. So I can send pictures of both of these to the these graphs to the group chat later if you guys need to look at them, or like we can open one of the notes things he has later to go over it.
Do you guys think the exam's going to be almost exactly like this?
So we know that they're going to be only 3 questions. He said that. We know that we're doing submit work, but unlike the practice exam, we're not submitting the work in Respondus. We're submitting it to a separate assignment that he detailed in his email. So I don't know if he'll have us enter answers into the actual quiz itself, or if he's just going to grade our work. It might be a combo of both. We don't know that for sure.
No, I know for sure. It's going to be like quiz 2, where it's just going to be a blank and you have to round to the nearest integer, and it'll be like 10 to the whatever value he chooses.
Okay, then it'll
be that in office hours.
All right, then it'll be that plus the fact that he'll obviously grade our work for partial.
I also asked if he would deduct based on work, like not showing steps or whatever, and he said that the work is really only there to give us partial credit.
Yeah,
he's not gonna like look through it and be like, oh, he didn't do it right, I'm gonna minus points here.
Oh, that's good to know, actually.
Yep.
All right, so using that information besides that, so my rundown of the quiz or the midterm is pretty similar to what we're working on now. He told us there's going to be 3 questions. There's only so much you can ask, and we know we have to touch on all topics, or at least all major topics. So question 1 obviously is going to go over homeworks 1 through 2. in terms of like, you know, or like original formulas for just regular doped silicon under no like extant circumstance, just silicon at equilibrium. And then it's going to have some resistivity stuff, and that's about it. Maybe some theory questions, but I kind of doubt that. Like, I doubt sole theory questions. More like computation plus theory, like we've been seeing.
We might have to like click the corresponding graph like we did in quiz 2.
Yeah, I absolutely like that. Would definitely make sense. And then question 2, I'm hoping he keeps them in the same order. Like question 1's like homework 1 through 2 topics. Question 2's like homework 3 topics, like that kind of thing. If he does do that, then I'm fairly confident that question 2 is going to be similar to what we're doing now, and it's going to be an MCDE. But my thing is, because we only have 90 minutes, I'm pretty confident in the fact that this MCDE question is going to be easier than the quiz 2 MCDE question.
Yeah.
I definitely
have a feeling it's going to be time. It's going to be time is going to stay, and
it's going to be time
the rest
dependent.
is going to go. Yeah.
So in this question right here, the one that we're about to go to, this one mirrors his example that he showed in class. I'm pretty sure it ends up with a linear relation at the end, like the AX plus B formula.
Yes. Yep.
But that's a good to know. He went over it in detail, which is good, because that's tricky. Like if you didn't know about that like possible solution set, you'd get it wrong. But once you've been informed of it, it's really, really easy to understand and use. So
yeah, that's my issue, is like, that's a general solution I haven't seen before, AX plus B.
Yeah,
I always thought it was like A e to the whatever, right? But so like, I asked him what would it be if time stayed and everything else got thrown out, and he said it would just be a constant. It would just be equal A. That's it.
Yeah, it would be. Yeah, that's tricky, but if that's the case, then good thing you said that on the record. Everyone remember, if time is equal to 0, then A is just going to be a constant, okay? Literally just going to be a number. I doubt he'll do that, because that's like a sketch solution, and that seems too easy.
He said more likely that the term that's whatever over tau and time would stay, and then it would also be A T plus B.
Yeah.
And I have a feeling that's what's going to be on our test. AT plus B.
AT plus B? Okay, interesting. So that doesn't reduce into the A e to the negative T over like tau. It doesn't reduce into that form. It reduces to
I asked him what would happen if the time term stayed and the N over tau term stayed, and he said it would be AT plus B. So. Okay,
cool. Good to know as well. I guess we can put all these on the formula sheet afterwards. That'd be good to have. All right, so let's move on to this.
If the light term ever stays, you just add it as a constant.
Right? It's always a constant. Yeah.
Just plus GL, or is there something with the GL?
It's GL tau, whatever your minority.
Oh,
is.
okay.
Yeah. Don't make the mistake I did on the last practice quiz. I did not treat. I forgot to multiply by the tau, and everything I did was wrong.
Oh, that sucks.
Yeah, simple mistakes. All right, for this one, we can start grinding through this one. I feel like this one's going to be the one with the most questions, because the PN junction stuff, I still feel pretty like that stuff's not that bad as opposed to the MCDEs. This is pretty complex in comparison. So looking at this, it has several steps, and we're expected to do all of them always. All right, so the question is, consider a silicon crystal, and we're looking at a p-type silicon here because our majority carrier is holes. 10 to the 18th at room temperature, kept under dark condition. You know that? Now that you know it's kept, and nowhere in the question does it say that light is ever introduced, your GL is equal to 0. You can know that immediately. Now, when we read on one end, x equals 0, we saw an x value. We immediately know that this is going to be spatially dependent. So you can also say that your time is going to drop out, because we know that it's going to be spatially dependent. And there are no permutations where time and space both stay, because we don't know how to do that. So since that's the case, our time dependence drops out too. So the partial with respect to n over the partial with respect to t drops to 0. Now we keep going on. So now our next steps to get our boundary conditions, which is part B. But our major steps to simplify first, which we've started to do. So at one end, x equals 0 of the semiconductor has excess carriers 10 to the 11th. The other end of the semiconductor, x is equal to 1 micrometer, has ideal ohmic contact, which enforces equilibrium. What that means, it sounds really stupid, but really what it means is that x equals 1 micrometer, your excess carriers are 0. That's all that means. So then now you assume there is no recombination inside the semiconductor. Find the steady state excess carrier. So now that you know there's no recombination inside the semiconductor, you can also know that there's no recombination rate. So if there's any question that asks for it, you could just say 0. That might be a trick question. But then he says, find the steady state excess carrier. He said steady state as well. That also tells you time drops to 0. So now we can simplify here. So the first things first is you always want to write out your full MCDE to start. So just the full equation, which is partial with respect to n over partial with respect to t is equal to d, whatever your thing is here. So this would be dn here, since our minority carrier is n. dn times d squared change in n over dx squared minus change in n over tau n plus gl. All right, we know a couple things disappear. GL goes to 0, time goes to 0. So now we have 0 is equal to dn d squared, that whole thing in the center, minus change in n over tau n. So that's our simplified version. And now we can take it one step farther and simplify it a little bit more, if I remember correctly. Where, yes, we can. So this was something that was important on the quiz 2, which I almost got wrong, but eventually was able to algebra my way through it. So whenever he makes us simplify to this stage, he always takes the coefficient on our big center part for the spatial dependency, the dn or the dp, and he wants it gone. He doesn't want a coefficient there. So what he does is he divides all terms by it.
Yeah.
And what that does is that produces 0. Obviously 0 but divided by anything is still 0. Then you have d squared change in n over dx squared. That stays. Now there's no more d on it. But now, this is the whole reason that diffusion length, right, that even exists. This is where that L comes from. That L that he just puts into the formula and pseudo explains that one time. This is where this comes from. So you still have the change in n, that stays. But now, if you divide by dn, you're going to have d tau n in the denominator. But what we know we know that ln is equal to the square root of d n tau n. So what does that mean? That means we can replace a denominator of d tau n with ln squared, because ln squared is equal to d n tau n. And that's the full simplification of this equation. And that would be what you would want as your answer for this. So that's just how you do that. Any questions on how we got around to the ln thing? Because I know that was tricky. I almost got it wrong.
Can you run back over that in 20 seconds for me?
Yeah.
Not 100% following.
Yeah. All right. So we start with the equation where we've eliminated time and we've eliminated GL, because GL is only present if there's continuous generation from light and we're in the dark. So you know that, so we have 0 is equal to dn times, the big thing in the middle for space, minus the change in n over tau n. That's what we're at now.
Yes.
Then what you want to do is that coefficient, that dn, we don't like it. We don't want it to exist where it does. So what we do is we divide all terms by dn. So now divide 0 by dn, stays 0. Divide the central unit by dn, it just loses its dn and stays the same otherwise. If you divide the change in n over tau n by dn, you get the change in n over dn times tau n, because that's just how division works. Divide.
Yes.
Yeah. So now what you do is you could technically leave it like that and it would technically be correct, but we don't want that. What we want is we want to introduce diffusion length into the equation, our ln. So how do we do that? We know that ln is equal to the square root of dn times tau n. So what we do is we can replace the denominator, which happens to be dn tau n, with ln squared.
Yeah.
Because ln squared would then be equal to dn tau n.
Yes.
Yep, there you go. That's what we did.
Flow.
That's all we did there.
I might be thinking wrong, but I thought that when we had NA, that we did it in terms of delta n. Oh,
We are
my-
doing it. We are
I'm
doing
dumb.
it. in terms
We
of
are
delta
doing it
N.
in terms of
Yeah.
delta N. Ignore me.
Yeah. No, that's fine. All right. Now that we have that, so that's just simplified there. Now we do specifying boundary conditions. So boundary conditions come straight from the problem's mouth. Rarely ever we have to do much like grinding to find your boundary conditions. It's really about reading a problem. Like it can be tricky wording, but in this one, it's pretty straightforward. So here we know that at x equals 0, our excess carriers, or delta n, is equal to 10 to the 11th. It just tells us straight up in the problem. Personally, I like to think about boundary conditions and initial conditions as points in my head. So in this one, or I'll write them down on my paper. So in this one, my point would be 0, 10 to the 11th, like 0, 10 to the 11th. Then the other boundary condition that we're looking at is when x is equal to 1 times 10 to the negative 6, or 1 micrometer. You have ideal ohmic contact, which enforces equilibrium. The word equilibrium means 0 when it comes to MCDEs. So now, when you're at some x value, you reach 0 carriers. So those are your two boundary conditions. You're working within this set. That's all it takes for that problem. So that would be full credit there. Then our next step, oh wait, does anyone have any issues with the boundary conditions, or was this one pretty straightforward? Yeah, it seems about right. This one's pretty straightforward. Some of them were trickier, like some of them are a little harder to specify boundary conditions, but this one was pretty obvious. If anyone still has, yeah.
Have we had a single one where one of the boundary conditions isn't equal to 0?
No, I don't think so. I'm pretty sure it always goes to 0 just to simplify things.
Okay.
Because if it's not 0, what would end up happening is B or A would drop out. Because you know that this one's simplification has 2 e to the x terms, or e to something terms. So if you didn't have a 0 as one of them, I'm pretty confident it would cause one of these things to drop out. It wouldn't cause one of them to drop out, and then you would have a more complex equation, and he wants to simplify it. Because when you have 1 that equals 0 at some, normally he has us have like a semi-infinite bar, which causes something to go to infinity, and that really causes stuff to drop out. But we'll see here. This one might not have dropouts, but it still should. All right. So that's just for the boundary conditions. And with regards to boundary conditions, there's another video on like where I post all these recordings where there's like an hour of boundary and initial condition discussion as well. If that's like a big point of contention, if anyone wants to go back and look at that before the exam, if they're still having trouble. Now we specify boundary conditions. Now we have to solve the simplified MCDE. So to solve this one, it's general solution, which is something you can put on your formula sheet for later. We'll do that later though. The general solution for a spatial dependent system is your delta n of x would be equal to a e to the negative x over ln plus b e to the x over ln. And that would be it here since we don't have any, we don't have GL. So now we have to use that and we have to solve for the a and the b's here.
Not for question 2.
No, for C, right? Solve the simplified MCDE and obtain the expression.
It doesn't have e's in it because the no recombination rate makes the delta p over tau p term go away. So the
Where?
The question 2, right? Of the practice quiz.
Oh, that's nutty. So this
the general solution is just ax plus b.
Yeah, this is okay. Yeah, no, I made that mistake. Yeah, I just talked about it too earlier, and I just let it blow past me. All right, make a note, everyone, because it just slipped past. When he says assume there is no recombination, that also causes another term to drop out. That causes the delta n over tau term to drop out into nothing.
Yep.
So now it's just 0 is equal to d squared, just equal to our spatial dependency function, which as, what is that? That's Andrew, right?
Yeah.
As Andrew just said, the spatial dependency equal to 0 is simply a linear relation, which is what 0 is equal to ax plus b, or not 0, but delta n of x is equal to ax plus b.
When we make the formula sheet, can you be sure to go over that again?
Yeah, definitely. I'm gonna need it too because I just missed.
Oh, are we waiting to make it? Because I'm making it right now.
Oh, you can make it as you go. No,
Yeah,
but I'm gonna go back over the whole thing anyway because there's still like a couple function like formulas and stuff that we'll need to specify. But all right, now we have that. So now we have this function, and now we're at part C where we have to solve the simplified MCDE and obtain the proper expression. So we've obtained the expression, but we have to solve for our A's and our B's. So we got to use our boundary conditions for that. So you plug in 0 here, and your n is equal to 10 to the 11th. So when you plug in 0, A zeroes out, and B is left. Thereby, B must be equal to 10 to the 11th. Then, when you plug in, x is equal to some small number, the value is equal to 0. So then when you do that, you do A times 1 times 10 to the negative 6th plus B. That makes the whole thing equal 0, because that was our other boundary condition. Therefore, we know what B is, so you just got to use algebra here to solve for what the A should be. So we can plug in B, say it's 10 to the 11th. 10 to the 11th. Then we can subtract it over, now we have negative 10 to the 11th divided by 10 to, or 1 times 10 to the negative 6 is equal to A, right? And that just gives us a big boy number. Was it 10 negative some to the 17th?
So if the light wasn't off here, would the general solution be AX plus B plus tau n dp or GL?
Yeah, it'd be plus tau n GL.
Okay, gotcha. So if light's on, you just add the tau GL.
Yep, that's not that bad, luckily for us. So the solution here, once you plug in your 0, the A ends up being negative 1 to the 17th, or negative 10 to the 17th. So this function ends up being negative 10 to the 17th x plus 10 to the 11th is what I have. And we can test the validity of this when we start solving. So if you look at question 2, part D, you can see that, at least for mine, it doesn't have a value to plug in at x.
Yeah, it's supposed to be 0.5 micrometers.
Got it.
That's what it is on the slides.
All right, we'll go for it. So using this function, you plug in 0.5 micrometers, which is just 0.5 times 10 to the negative 6th. So you do negative 10 to the 17th times 0.5 times 10 to the negative 6th. And then you do plus 10 to the 11th. Okay. Well, yeah, 10 to the 11th, and your number just ends up being 5 times 10 to the 10th positive. So there's that. When you get to this part, assuming your formula is correct at this point, it's straight up plug and chug, which is not that bad. Particularly in this case, if we end up actually having one where it's a linear solution, plug and chug for a linear function is not troublesome at all. So for this case, my excess minority carrier density at, half a micrometer is 5 times 10 to the 10th. So there's that. Out of curiosity, on his PowerPoint, is his question 2 identical to this?
Yeah, all these questions are the exact same as the PowerPoint.
Did the PowerPoint have 5 times 10 to the 10th?
I'll check real quick.
I can open it as well if needed.
Yeah, he has 0.5 times 10 to the 11th. So yeah.
Yay. Okay, cool. So we solved that correctly. That's good to know. All right, so we did D, and now we got to do E, which is something that I'm a little shaky on when it comes to diffusion current stuff, but I might be able to solve for it here because this is linear. So this makes it a little easier to solve for the slope. So the formula we're working with here for diffusion current is simply Q times dn times the gradient of n, or whatever that symbol boy is. And the gradient of n happens to be the slope in this instance for a linear.
Yes.
So it's Q times dn times the slope. And we can do the slope with our boundary condition values. So our boundary condition values, we can start. So it's, for slope, it's, y2 minus y1 over x2 minus x1. So if we do 2 minus 10 or 0, 0 minus 10 to the 11th, you will get negative 10 to the 11th. So there's your top, your numerator, and then your denominator. If you do, 1, you do 1 times 10 to the negative 6 minus 0, you still get that. So you have negative 1 times 10 to the 11th divided by 1 times 10 to the negative 6th. You get negative 1 times 10 to the 17th. So there's your slope. That's a number for your slope. So you're going to have a sign here. It's obviously going to be negative. So you take that number, you multiply it by the dn, which he just gives right there to be 10. You then multiply that by your constant q, which I use as 1.602, but 1.6 is fine. 1.6 times 10 to the negative 19th. And you get negative 0.16. Is that the correct thing he had in his slide?
1.6 milliamps. You might be off by 1 decimal.
Why is that? Wait a second. What did he?
Did you plug in 10 for DN?
Yeah. Did he just plug in 10, or did he do some manipulation on the unit?
No, just
Did he have a discrepancy for the slope? Is his slope negative 1 times 10 to the 17th?
the slope is negative 10 to the 15th. It just should be equal to your A value. This one's a little tricky.
Oh, wait, you're right.
Yeah, you're supposed to take the derivative of the general solution before you plug in the 0.5 micrometers.
Oh, boy.
As far as I understood it.
So, oh yeah, I see it's at 0.5 micrometers. So we take the derivative of it first, but the derivative of this, with respect to x, just drops out. It doesn't become dependent to the micrometer, does it?
No, it doesn't. Exactly. So it doesn't matter that it's at 0.5 micrometers.
So it is.
It's kind of tricky though. Wait,
but our A values, how is this A value 10 to the 15th? Or is this negative 10 to the 17th?
Is it?
Yeah,
I got my A as negative 10 to the 15.
What did you do for it? What did you divide 10 to the 11 by?
Oh, it's because he wants you to plug in a micrometer. So should be 10 to the negative 4, not 10 to the negative 6, because you change it to
reference to centimeters. Yeah, okay. That's what I knew it had to be something with a unit manipulation somewhere.
Yeah.
All right, that's big. That's something everyone needs to remember. Our reference
he's
is
done
no
that
longer
on every single quiz.
Our reference is no longer meters. It is now centimeters. Treat everything as so. All right, so because of that, now I see where that came from. So yeah, so I was off by, what, 2 orders of magnitude? Yeah. Yeah, because of that little sign flip. So that's good to know. All right, does anyone have any questions here? There might be questions here because we goofed, or more accurately, I goofed. Does anyone want to ask any clarifying questions to me or Andrew for this part?
Why do we take the derivative again?
Because I guess because you said
formula.
so, yeah.
Because it's just the formula of J diffusion.
Yeah, so the formula of J diffusion is the formula is Q times your D value times the gradient of your function. In our case, since we have a linear value here, a linear value, just, take the derivative of it and you just get, A. So that's what Andrew said, and that's the correct answer.
Okay.
Yeah, so that's what we do for it. Probably in our best interest to jot that down on the formula sheet later. You can write down, like, literally for drift diffusion. You can write down drift diffusion cases per solution for an MCDE, because I guarantee you we're only going to do drift diffusion for the MCDE part. We might do. Yeah, drift diffusion. Yeah. Wait, yeah, diffusion current. Why do I keep saying drift diffusion? Okay. Yeah. I don't remember. Does anyone remember on homework 4 if we did any diffusion or drift current?
I don't think we did.
Yeah, I don't think we did. I think our best was like voltage and electric field stuff. So I don't think you will have to use it there. So we're moving on to the next one, which is the fabled Pn junction. Look at how beautiful that is to read.
Wow.
Look at those pixels. All right.
Did you take that on a Nokia?
Bro, please. It's on an iPhone 10. It's on an iPhone 10, homie. It's my monitor's fault.
I'm joking.
Yeah,
Same.
it's all my monitors. It's my monitor's fault.
It's
All
still
right.
readable. It's fine.
Yeah. I was gonna retake it, but I saw it was readable enough, so it's fine, as you said. All right. So PN junction is a bunch of formula plug and chug. So I'm gonna whip out the formulas before I even start reading this. Because for PN junction, a little bit of theory, a lot of formulas. And when I say a lot of formulas, it's 3 formulas total. And there's some sub formulas if you want, but I refuse to use them because they're stupid. So we can start now. Let me fold this back so this isn't in my way anymore. Pop. All right. First step first, consider a symmetric PN junction. Symmetric is important. That tells us, you know, that both sides have the same level of length. So we're not going to see any wacky stuff with regards to our, what is it? With our, how do I forget the name of this? Our graph of the Fermi level, whatever that thing is. I said it like 10 times for question 1. All right. Consider symmetric PN junction at equilibrium. Both N side and P side have the same doping density given there, 10 to the 17th. Assume both electron and hole mobility to be the same given as 1,000. Cool. So it looks like we have very little information, but the trick is that's basically all we need to just fill in these formulas. So find the value of built-in voltage at room temperature. The equation for built-in voltage is yet again the fabled KT over Q quantity, which I take to, whenever I see it, I take it as 0.026. So that's a constant in my head. I just leave it as that. And then ln of Na times Nd over Ni squared. So that's what we're working with here. So the implementation of the VBI formula here, the built-in voltage formula for this question, looks as so. It is VBI is equal to 0.026. That's a constant, never changes. Unless the temperature changes, then it does change. Of ln of 10 to the 17th squared over 10 to the 20th. And it's 10 to the 17th squared because, you know, Na times Nd, if they're the same value, is equivalent to simply squaring something. So if you do that, and, you know, 10 to the 17th squared is also, what, just 17 times 2. So you're going to get 10 to the 34th divided by 10 to the 20th, which is going to yield you 10 to the 14th. So your ln of 10 to the 14th, I'm going to give a fancy boy number of 32 point something, and then you multiply that by 0.026. And for this question, we have a built-in voltage of 0.838. You'll notice that that is the same exact voltage value we got for question 1 on homework 4. That is because if you have a symmetric PN junction that has identical doping density of 10 to the 17th, that's always going to be the same exact number. It just so happens that he used the exact same question from the homework here.
Can you repeat that? You went full robot for me.
Did I? How far did I get before I went robot?
Something about being symmetric, and then it went robot.
All right. So you'll notice that the built-in voltage here is when running the math through the formula, pretty basic formula, no problems there necessarily. You get 0.838 volts. That happens to be the exact same number that we saw in homework 4, question 1. And that's simply because he obviously pulled the exact same trick. It's symmetric, and both sides have the exact same doping density. And the same doping density, you know, is going to make the same voltage. So that's not saying that this is some type of constant, but if you see a problem that has this, you know, problem statement, you can technically just know all the answers already, if you feel so inclined. But so now we solved for part A, easy peasy. Now we got to solve for part B. How the built-in voltage will change if temperature increases beyond room temperature. I got this wrong on the homework because I'm a Fapega. So I personally, I looked at the VBI equation, and I saw that it was temperature dependent through the KTQ function, or the KTQ quantity. So I'm like, okay, T's in the numerator. If T goes up, the overall built-in voltage should go up, right? No, it does not. Because I forgot that we were working with semiconductors here. We're not working with metals. When the temperature of a semiconductor goes up beyond room temperature, its resistivity decreases because it generates more free carriers. Because of that, the built-in voltage goes down. So just remember the built-in voltage goes down when temperature goes up. That's basically all you need to know. And
Yep.
for the explanation, just what I just said is basically it. So there's that question. All right, and then part C is find the total depletion width for this PN junction diode. There are two formulas. Well, actually, there's technically 4 formulas for this one. I personally, wait, never mind. I'm talking about the wrong thing. There's 3 formulas for depletion width, 2 formulas for max electric field. So for depletion width, there's 2 methods you can do for it. So depletion width is equal to the depletion width on the P side plus the depletion width on the N side. But those, like, that's like an extra weird quantity. You can turn the whole equation into one thing, and it becomes the depletion width net is equal to the square root of 2 epsilon silicon, like epsilon of silicon, over Q times VBI times the quantity 1 over Na plus 1 over Nd. So it's just it's literally yet another just plug and chug. The only trick in this one is we're very, very used to just like looking at something over Q and just saying, oh, it doesn't matter, and just turning it into like 0.026. But in this case, you can't say it's 1 electron volt. In this case, you got to put it into the 10 to the negative 19th. If you treat it as an electron volt, there's a lot more, units. You'd have to go all the way back and like mess a bunch of stuff up, and we don't want to do that. So in this case, leave the Q denominator in under the square root as 1.6 times 10 to the negative 19th. Like that's something that's very, very important. So beyond that, epsilon is a constant. Epsilon of silicon is a materially dependent parameter. I think it was 11.8 times 8.85 times 10 to the negative 14th farads per centimeter or something. I think that's permittivity of free space. Well, it's 11.8 times permittivity of free space. Either way, the formula overall, we can do this math, is going to be the square root of 2 times, that constant over 1.6 times 10 to the negative 19th times our built-in voltage, 0.838, times 1 over 10 to the 17th plus 1 over 10 to the 17th. And then we will solve for this. So I'll run through this real quick and just chunk it into the calculator like a legend. So 2 times the big boy number. Actually, I'm going to work this out real quick because this epsilon's always going to be the same. And he writes it out stupid like, or odd like at least in his thing. I feel like he should have reduced it. So I'm going to reduce it now for us so we can put it in our formula sheet. Reduced with 14th. All right. Epsilon for silicon. This is a value you should all just like have written down, and we can either write it down later or you can write it down now if you're making the formula sheet as you go. Epsilon SI is equal to 1.044 times 10 to the negative 12th. That is epsilon silicon. He writes it down as epsilon silicon is equal to 11.8 times the permittivity of free space epsilon naught. That, when you do that, is equal to what I just said. So that's easier, because when I did the homework, I plugged it in the long way, and I feel like that's a waste of time. Better to just have it pre-known. So you take that, you multiply it by 2, you divide it by 1.6 times 10 to the negative 19th. Then you do 1 over 10 to the 17th. And then you do that twice, technically. Plus yourself. There you go. You got 2. Then you do times 0.838. Then you take this times this. Then you do this. That feels wrong. So I got 5.9 times 10 to the negative 15th. That feels far too small. Let me think about this.
Was it question 3?
Question 3, part C, when we're using the depletion width formula.
I got 14.8 times 10 to the negative 6th.
Yeah, so that should be right. So run me through the numbers you plugged in. So you plugged in like 0.838, obviously. You plugged in, 10 to the 17th for both the denominators. You did 2 times the epsilon value, right?
Yes. divided by divided by chart Q.
Yeah.
10 to the negative 19 square root.
Yeah, I did square root it and it got me the 12th number. There's definitely a discrepancy on my part somewhere.
I did whatever he had down for epsilon, 11.8 times 8.85 times 10 to the negative 14.
Yeah, let me check something real quick to make sure. Yeah, it's 8.85 times 10 to the negative 14th. Yes, times 11.8. I did that proper. And I got that value. I took that value, multiplied it by 2, correct? So let's take this instead. Wait a
How
second.
did you combine your NA and ND?
Never mind, I found the problem.
Okay.
It's a calculator error, obviously. Why wouldn't it be? 15th. So that times this. Yeah. You said you moved it to micrometers, right?
What did I move to micrometers?
Because I got 1.4 times 10 to the negative 5th. So you just got 4.
Oh, yeah.
Yeah, so that's that. So from what I've seen so far with regards to the answers to depletion width questions, it's almost always on the order of micrometers. So that's a pretty decent way to check your answer. You should make sure that it's like some reasonable value in micrometers. That's just like a potential rule of thumb. That might not actually be true, so don't take that to super heart. But all the examples we've seen so far have resulted in micrometers. All right, now we did depletion width. Now we got to draw the energy band diagram. So this is that tricky energy band diagram I mentioned earlier. So your holes or your P side has a higher energy band. Okay, actually, I'm gonna explain this a little bit better. So when you're drawing this, you should start by drawing your EI level, your straight dashed line. So to draw this, you start with your straight dashed line. That's your EI, label that as EI. Now, something we know from the beginning of this class, from homework 1, is that if your Fermi level is below EI, then we're talking about a majority carrier of holes. If we're talking about a Fermi level higher than EI, we're talking about a majority carrier of electrons. That principle is what ends up happening here. Because believe it or not, all a PN junction happens to be is 2 pieces of doped silicon that are interacting with each other. So what happens here is we draw that accordingly. So start with that dashed line. And what we're going to do is we're going to work about this in thirds. So for the first third of that dashed line you drew, you're going to draw the solid lines if this dashed line were if this dashed line happened to be, wait, is this EF or EI? I think I mixed it up. I think that's supposed to be EF. Let me check something. I think the dashed line might be supposed to be EF. Yeah, it has to be EF. Scratch that. The dashed line's EF. It's not EI, but same thing. All right. So not the same thing. All right. So now that you have this dashed line EF, we're going to work about this dashed line in thirds. So this is a decent way to think about how to draw these proper each time. So when we're talking about a N-type silicon crystal, the Fermi level is below EI. So what you do is you draw a solid dashed line on the first third of your EF line. You draw below the EF line, relatively close to it, a solid dashed line, and then above the EF, relatively higher than it, like farther away than it than you just drew, you draw a solid dashed line, or like a solid line. Then on the leave the center third like empty, and the second third empty, and then go to the final third of that line. Draw a solid line close to the top of the EF, and then draw another solid line farther away from the bottom of the EF. So when you look at it, if you go across, you have 2 dashed lines where they're higher net, and then you have 2 solid lines that are higher, and then you have 2 solid lines that are lower. But the straight dashed line is straight across between them. Then what you do is you draw a solid line that slopes down and connects the top bottom and the top bottom. And then you have to draw EI, which happens to be a dashed line that follows that same curve. So I'm about to take a picture of what I just drew and send it to the group me. And tell me if what I just said made a lick of sense explaining it through my mouth. Because it may not have. Alright. I just sent that picture, so you should all receive it momentarily. Tell me if what I just said lines up with what I just drew. It's this, by the way. This is what it looks like. You have your solid line here, which is the Fermi level, your EF. Then you have your solid, this is like, that's what, the reason I said think about it in thirds is because this is what he's explaining right here. Here is your P-type, here's your N-type. When you make it so the EI or the EFs line up with each other, and it's a straight line, obviously the P-type is going to be pushed up and the N-type is going to be pushed down with relation to this central EF. And then your EI, which used to be a straight line down the middle of both of these, ends up following the shape of this curve we have. So it would start here, go down at a 0 point, then follow a line here. And that's what it would end up looking like.
Right.
So this is what we have to draw.
Okay, so repeat for me again, what determines which one follows the shape of the curve?
Which what?
Or is it just always EI? Between EI and EF, is that always EI that follows the shape of the curve?
Yeah, EI changes, EF does not. Because EF is a constant value with regards to across the PN junction. Well, graphically, it's a constant value. It stays the same.
Yeah.
Technically, it's the same value across the PN junction, assuming that we're talking PN junctions with identical doping. I don't remember if doping changed. It should change it slightly, but either way. So since we're working with 10 to the 17th on both sides, our EF value is constant across the graph that we draw. But in reality, on the P-type side, it's the negative value of the number, and on the N-type side, it's the positive value of the number. Because relative to their original graphical representation, it's below EI. And that's why I'm kind of mad he didn't put EI here. Because EI actually starts up at the center of the P-type solid bars, goes straight, follows at the center of the curve bars, intercepts a 0 point at the EF at somewhere, and then gets to the center point of the solid bars for N-type, and then follows that as a straight dash line below EF. So you can tell the EF is below the EI on the P side. There's a 0 point between them. And then the EI is above, or EF is above the EI value on the N side. And that's what yields you your sign values. That's something you could just know. You don't need to compute that, because every time you compute it, it should still be positive. That's just something you need to know relative, like just knowledge-wise. Let's go back to this one. All right, we just did the depletion. We just did the energy band diagram. Now finding the value of EF minus EI at the junction point. Let's go back to what I just said about the EI. How you see it tracks. It goes, stays at the center point of the solid lines, stays at the center point of the this curves the junction. This is where the junction's happening, where the depletion is. Stays at the center point of this, intercepts the 0 somewhere. And then it goes down and stays at the center point of the solid bars here. So what do you think EF minus EI happens to be at the junction point, which is the center of this junction point curve? It intercepts 0. It's 0. EF equals EI. It equals 0. So that's something you can just remember. If it ever asks at the junction point, I'm pretty sure it's almost always 0 at the junction point, because of the nature of how it's graphically represented and just the nature of how it works. Yes. That. Cool. All right. There's one last question about resistivity, if I remember correctly.
Yeah.
Hey, is the freeze out region, is that at low temperatures, or is that at the right end of the graph?
Freeze out is at the far left. So freeze out's from freeze out, obviously 0 Kelvin, obviously.
Okay.
But I think it actually has a range. It's not just 0 Kelvin. It's like 0 Kelvin to like 15 Kelvin or something, like small values.
And then the other side's extrinsic.
It goes so for intrinsic, it's just freeze out and then intrinsic. And then the curve we're most interested in is the doped curve. The doped curve is freeze out, extrinsic, intrinsic. It has 3 ranges. Extrinsic is when that bump happens.
Are you sure?
I'm pretty sure because it's the extrinsic range, right? Yeah, because I have it graphed. There was a question about that on the quiz 1 that we took.
Yeah, I could have swore the extrinsic was on the far right side, but I might be wrong. I think I'm probably wrong.
Well, because think about it this way. We call it an extrinsic range because it's different than the intrinsic graph. The only difference that the extrinsic graph has from the intrinsic graph is that a small portion of, or like a portion of temperatures from room temperature to a higher temperature, where its resistivity momentarily increases. Thereby, eventually, once you get past that to where the intrinsic carriers are being produced at a rate that's comparable to the amount of carriers that were already produced by the donor or the dopant, then you go back to being intrinsic almost immediately. That's why its extrinsic range is in the middle and intrinsic's on the outside, right? So that's just a quick clarification. Find the value of resistivity at the junction point. Okay, there's a formula for this somewhere. Let's see, what did it look like? Actually, pretty sure it's probably the exact same thing. Let me see something. That's that. Oh, I'm a dummy. My homework's right there. Oh, I probably did it right here somewhere. Where is it?
So just checking, the practice test itself doesn't give us any answers, does it?
Nope.
It's just his slides.
Yeah, I think his slides give answers.
Cool. I will not be taking it then.
Yeah, we're doing it right now. This is what it is.
Exactly.
Yeah,
This is the only time.
Exactly. All right, here we are. I found the formula. The formula for resistivity in a PN junction is identical to the formula that we've been using for resistivity. So it's the same thing. So what we do for this part is, we did this in the homework, so I can just look at that example as well. So when it says at the junction point, in the homework, the junction point was x equals 0. But either way, this is how it's going to be. So I'm going to go back to the, so for this one, it's good to have what he has up here to explain. This is what we're looking at. This literally the exact same thing. Look, 10 to 17, 10 to 17th, and this is symmetric. So this is the exact problem we're looking at right now. And this is the exact model of the PN junction that we're looking at right now. So the junction point is right there. At the junction point, P and N are equal to exactly, okay, at the junction point. So here's something we need to know real quick, like a foundation knowledge about the PN junction. At any given point in the PN junction, the law of mass action holds. What does that mean? That means if you do the number of, is this holes? Yeah, holes times electrons will equal 10 to the 20th. Go over here, holes times electrons will equal 10 to the 20th. At here, holes times electrons will equal 10 to the 20th. And then over here, electrons times holes will equal 10 to the 20th. The law of mass action holds across the PN junction at any location. And knowing that means we know the answer. Because remember, for resistivity, everything's given to us in the question except for the carrier densities. And it seems impossible. How are we going to solve for 2 carrier densities, right? We know 10 to the 17th on each respective side, but it's not 10 to the 17th at the junction. What we know is that, look, at the junction, P is equal to N is equal to 10 to the 20th. Thereby, 10 to the 20th divided by, well, 10 to the 20th. It's just 10 to the 10th. A 10 to the 20th divided by 2 is obviously not the right number. So it's a different operation that you perform.
Yeah.
It's 10 to the 20th divided by 10 to the 10th is what you're doing to solve for it. But yeah, so it's 10 to the 10th.
Why do we have the 10 to the 3rd? Like, where's the 10 to the 3 come from?
Oh, okay. Quick trick there. Law of mass action is your carrier densities multiplied to each other is equal to 10 to the 20th. So if you have 10 to the 17th times, x, or times, okay, we'll just do this proper.
Oh,
10 to the 17th times n equal 10 to the 20th, divide 10 to the 17th. You're going to get n is equal to 10 to the 20th divided by 10 to the 17th. That equals 10 to the 3rd. That equals 1,000. Checkmate. There you go.
Gotcha.
And that law of mass action holds everywhere on the PN junction. So that means here,
Right.
that means it's equal. So it's 10 to the 10th times 10 to the 10th is equal to 10 to the 20th. Thereby, you know your values. So your resistivity is going to be equal to 1 over, Q times What's our, what did you say our mu value was here? It's 1,000 here. Cool. Literally the same question as what we're about to look at. I'm just gonna scroll down. This is the answer. This right here, this one. So the 3.125 kiloohms. This is the answer. I looked at the values and I'm pretty
Is
sure.
that always what it is at 0?
Pretty sure, yeah. Well, okay, no. I'm not gonna say at 0. I'm gonna say at the junction point.
Oh, right. Yeah, not 0.
Yeah. Because relatively, like in our homework, they named the junction point 0, but like they could just as easily name like the farthest left portion of the p-type silicon 0, and then you'd be wrong. But yeah, as I said, the law of mass action holds across the Pn junction, I think, in all instances that we're used to so far. Thereby, knowing that means at the junction point, it should always, that resistivity is a constant.
Cool.
Lit. All right, well, that's the entire test. So that's all the questions. That's everything. So that seems more manageable.
Yeah.
Than it actually.
It's a lot more manageable.
Yeah,
than it was on the other ones.
Yeah, even the MCDE should be a simpler case.
Yeah. I was thinking I was going to have to go back and memorize all those different word problems. Not word problems, like definitions for the first quiz. But
nah, who needs to do that?
I know, right? Oh man, I can just figure out how to work the problems now. This is so much better.
Reworking homeworks as Alex was doing, and like reworking, just going through slides is good. But I personally think that these study sessions are pretty easy stuff. When you go through these, just talking about something with someone kind of ingrains it in your head.
Yeah.
So
how many formulas for the width? What is it? Width dependent? There's like 5 different formulas. How many are you guys gonna write down on your formula sheet?
Wait, what'd you say? The depletion width?
Yeah, depletion width. That's what it is.
I'm not gonna write that many down. So I was wrong when I said that. There's technically 2 formulas, 2 sub-formulas, 1 general. You're only really gonna want the general formula for depletion width. Now, in this question 3, he didn't ask anything about the electric field. I recommend looking over homework question 2 from homework 4. Because that's definitely more like the type of thing he'd give. Like he's definitely like he doesn't just give you the electric field and all that information about electric fields and not use it. Let's be real. So I would write that equation down just in case. But
the 1/2 Emax depletion width.
What? All right, so I'm gonna go through the formulas real quick. Starting. I'm gonna start my own formula sheet as well, and we can go through that as it comes. Where the hell did I put my formula sheet? It was just here. Is it in my book somewhere? Yes, it is. Cool. All right. All right, gotta pluck a piece of paper out somewhere. Come on out, paper. All right. So we'll start by just hitting up homework 3 formulas just to begin, just since we're already here. All right. First things first, your built-in voltage formula. There's 1 formula for it, no tricks for it. You just write it down. So our first formula, and you can section off your formula sheet however you want. I'd recommend writing down what the formula is useful for. So like write down like Pn Junction formula or whatever, like the main ones. There are formulas that are useful across all variants, all questions, like law of mass action, that kind of stuff. I wouldn't necessarily specify those. But so to start, built-in voltage is VBI is equal to KT over Q times ln of NA times ND over NI squared. That's done for that one. Depletion width, there are technically 2 formulas, 2 sub-formulas. I would write down 1 general formula, which is given. That would be the large big boy square root one. I wouldn't keep track of the others. Actually, never mind. Yes, I would. There are 2 I'd like to keep track of. That would be the 2 sub-formulas of the pre-general formula. Then we'll talk about those in a second after we get the main formula down. So 2 epsilon silicon. So 2 times ESI over Q times VBI times 1 over NA plus 1 over ND. Done. So there's that formula. Now the sub-formulas for depletion. Because in the homework, he asked us the depletion on the N side and the depletion on the P side. If we need to do that again, we need to know the specific formulas for it. There are formulas for it. The depletion width for the N side is equal to NA over NA plus ND times the depletion width. W, like the one we've already, like the general depletion width. All right. And then W, or depletion width on the P side, is equal to ND over ND plus NA, right? Yes. Times the depletion width that we've already got a formula for. So those are the sub formulas if needed. There's a chance we don't need them because honestly, he gives us 90 minutes, 3 questions. Everyone's going to sink most of their time into the MCDE question. He's going to make this one a little simpler. I can already guarantee that most points will be lost on question 2. So you can focus energy somewhere else for that with regards to that. All right, we're still going to write down the electric field max question just in case. But also, if you don't have it memorized, I would also detail what epsilon is, what ESI is numerically. Since it is a constant, he might give it to us on the test, like in like that thing, but don't count on it. So just write it down. So you can write it down in one of 2 ways. Probably the best way is to just write it down as 11.8 times 8.85 times 10 to the 14th, negative 14th. There's that. And for my, in terms of my formula sheets, I like to write down like the relevant units for each formula, just in case, just in case I fat finger it or something. So like you have volts, and then for the depletion widths, you should write like commonly micrometers. But there's that. All right, now we've passed that. Now we got to do the Emax formula. So there are 2 formulas for Emax. I prefer the simplified formula. The simplified formula, in order to use this one, you need to have the depletion width calculated already. So because of that, I'm gonna say both formulas, but just like I like the simple one more if I can use it, if I've already calculated depletion width.
I mean, is there a situation where we wouldn't have already done that though?
I mean, who knows, man? If he just doesn't ask a question about depletion width and asks for electric field, then yeah, that could happen.
Just calculate anyways.
Yeah. You can. Because if you can calculate, that's the trick. Because if you can calculate the built-in voltage, you can calculate depletion width.
Yeah.
So you're fine. So in pursuit of that, I'm just gonna write only the simple formula down. So the simple formula is 2 times VBI divided by the depletion width. That's it. That's your max electric field. Cool. That's everything for PN junctions. For formula sheets, I don't know if you're allowed to draw stuff. Like, I don't think you're allowed to draw the energy band diagram or something. You might be able to. That's like something you email him for, but that's up to you if you want to do that. But I'm not going to draw that. Someone was about to have a question. Okay, then. All right, now we can move on. We'll just go backwards. We'll go to MCDE formulas or MCD relevant formulas, or at least in this part, I'm just going to read off my formula sheet from the last quiz. So you're going to want your drifts and diffusion currents just in case, but it's really mostly just diffusion current. I don't think we've had to use drift like once. So because that's the case, I would just write down the diffusion current. So the diffusion current formula is just Q times your D value. You can write D or DN or DP. Just make sure you change it when the time comes where you actually know your minority carrier or majority carrier. DN times your gradient of your minority.
Are we back on number 1 now? Or are we still on the
we're just doing formulas.
Okay.
So when it comes to this question, I'm on my quiz 2 formula sheet right now.
Yeah.
And you're right to remember like homework 1, 2 had diffusion current and like that and drift current and stuff, but for the purposes of this midterm, I can almost guarantee that question 1 will have nothing to do with the currents. It'll focus on general law of mass action and general law of mass action, doping, resistivity, and the relation to intrinsic silicon. Where question 2, where the MCDE is, will focus on the drift current.
Yeah.
Because we haven't really. It makes more sense for him to do drift current there because drift current has more of an application there than it does in just regular silicon.
Right.
So there's that. And then here's something we could get down just in case, that being the law or Einstein relation. We haven't had to use it in a while, but it's something nice to have just in case. It just relates a bunch of stuff together. It's really useful. Your Einstein relation happens to be whatever your D is. I default to Dn when needed. So D over your mu n is equal to K sub BT over Q. So there's that. Remember that K thing, that room temp is equal to 0.026. So that's just something to know. All right, now we can get down. We can do the Quasi-Fermi level. We can do Quasi-Fermi level formulas since we're on MCDEs. All right, to solve for FP, your Quasi-Fermi level for your holes, is FP is equal to EI minus KBT ln of NA over NI. That's all you do for that. And then your Fn is equal to EI minus KBT ln of ND over NI. Now, oh wait, fuck, I messed up there. The second formula is EI plus, not minus. I was about to make the comment on that. So because of the method by which we graphically represent energy band diagrams, right? That's what they're called. Yes. That's actually expressed here because obviously you're not going to get a numerical value for EI in this question. You're going to get FP is equal to EI minus some electron volt value or plus an electron volt value. And the reason I say minus or plus, so when it comes to holes, we know that if you have something with holes as a majority, it pulls the Fermi level below the intrinsic or the EI. And then we also know that if you have a majority carrier of electrons, it pulls the Fermi level above the EI. So that's the result of the negative and positive signs in these formulas. So FP has the EI minus and FN has the EI plus. So that's just something to know. It's not super.
Question.
Yeah.
So if you have an N type, so your minority are holes, right?
For MCDE or just in general?
Well, I'm talking about for finding Fn.
Yeah.
You do ln of what? N over Ni? Or what is it that you do over Ni?
So you're saying
it changes.
So you're saying. Oh, so you're saying for if N's the minority or majority?
Yes.
So you want to know how to do Quasi-Fermi level for minority carrier?
Well, is that what he's always going to ask?
So when it comes to Quasi-Fermi levels, he's always going to have you do both of them. Otherwise, what's the point of a Quasi-Fermi level? He'd just have you do one. So because there's two Quasi-Fermi levels in every, in an MCDE, there's two Quasi-Fermi levels because there's no more a majority carrier necessarily, like not to the same difference, because like if you have like an N-type piece of silicon that's 10 to the 17th doped, and then you expose it to a bunch of light, it'll still generate a bunch of holes. The majority carrier won't change. It'll still be 10 to the 17th, but it can generate like a lot of holes. Like it can generate up to like 10 to the 17th holes. It'll generate up to the carrying capacity, which is GL tau N or GL tau P in this instance. So because of that, as I said earlier, in like regular doped silicon with no light, there's one Fermi level. But when you add, excess minority carriers, it causes them to be comparable. Thereby, there's two Fermi levels now. They separate away. Because of that, let's say, for example, we're doing an MCDE where we need to calculate the Quasi-Fermi levels of an N-type. Thereby, holes are the minority. So to calculate your Fn, it's just your given ND. You just plug the ND into the numerator and you're good. Like in the question, it'll say 10 to the 17th. You'll be good. Done there. Then on the FP, it'll have you calculate the Quasi-Fermi level at its variable position, whether that be from time or space. So you'll have a number that you can just plug in, and you'll get that number from the simplified MCDE formula. And then you'll just plug that in as the numerator, because at that point, that is the amount of carriers you have of the holes or of the minority.
Okay.
So for these ones, in order to calculate Quasi-Fermi levels for MCDEs, you need a specific point, whether that be a point in time or space. And that'll be detailed in the question. So
And the other one is just going to be either ND or NA, whichever one it gives you.
Yep. Whatever's the majority is pretty easy to calculate that Fermi level.
When can you use mass action to find the other one?
Mass action is only viable in silicon that is under quote unquote equilibrium. So silicon is not under equilibrium if you're, bombarding it with light. That's no good. It's variable. Silicon, although that is doped and sitting on my desk in a dark room, had to qualify that there, is in fact under equilibrium because nothing's happening to it. It's just chilling. So the silicon on my desk has a constant relatable relation. Yeah, what the fuck is a relatable relation? Has a constant relationship between its carriers, and it will equal Ni squared.
In our last quiz, when did we use the law of mass action?
I don't
because
remember.
I'm pretty sure we used it, but
we did. We used it for parts of, because there were portions of the silicon that were in fact like specified to be like a non-doped variety or something. It was a spatial dependency somewhere.
So if your minority are holes,
yes, then
you're supposed to use the law of mass action to find. So if minority's holes, then that means your electrons is going to be equal to the donor, the ND, which is going to be given probably.
Yes.
And then you use law of mass action to find the holes if it's like at equilibrium.
Yeah. So I can so let's take the question we did last time, for example. You guys remember the graph, the green graph with the peak at x equals 0 and then it drops off pretty quickly on both sides from the quiz 2?
Yeah.
Peak at x equals 0.
Yeah.
Yes.
Yeah. The green graph. So that was the right answer. Now I can explain where on that graph you can and cannot use the law of mass action. You cannot use the law of mass action at x equals 0. You can use the law of mass action at infinity in either direction. Now there is a certain point at which it reaches there's an actual specific position where it equals, where you can actually use the law of mass action. And that will be the point where excess carriers are 0. The moment excess carriers equals 0, law of mass action applies once more.
Okay, I remember now when we used it. It's like, if it was like find the electrons at x equal 1 meter, which is basically infinity for us. So then you can use law of mass action.
Yeah. The moment excess carriers drop to 0, law of mass action once more applies.
I don't really know. What does that mean?
Excess carriers, the whole point of an MCDE is to solve for, that change in N, change in P, that is your excess carriers. That's what you're solving for.
Okay.
So the moment that number is equal to 0, the law of mass action applies in that instance.
Oh, okay. Sometimes it starts at 0, right?
Yeah. Sometimes it does the opposite. Sometimes the law of mass action applies for, some infinite time while it was in the dark, and the moment the light turns on, the law of mass action is a no-go anymore.
Okay.
Yeah. So that's that formula. So we got the Quasi-Fermi levels down. Well, we've been talking about the law of mass action so much, and it's basically has applications in all questions. So everyone write down NO times PO or N naught times P naught is equal to Ni squared. Now, N naught and P naught can change. Like N naught could be equal to ND in some scenarios. P naught could be equal to NA in some scenarios. Just remember that it's just whatever your carriers are given at that time. Like if you're given ND, then your N is going to become 10 to the 18th. If you're given NA, then your P is going to become NA, that kind of thing.
Yeah.
Like that's just something to remember, like what symbols can be equated when.
Did he have a lecture where he went over the latest quiz?
Latest quiz? Probably. Actually, he definitely did. Whenever he does the quiz going over stuff, I don't pay super big attention to it because I don't see too much value in having it explained necessarily. It's only best if my preferred method would be if you just posted quiz solutions, which he might do. I don't know if he does that or not, but For
It's
me,
such a pain that it's in the lockdown browser still.
yeah. For me, I just know for a fact that like when I mess up or whatever, like I know I messed, like the moment I submit my quiz and look over my work again, I find all my problems like almost immediately.
Yeah.
That's just how it is sometimes. It's sad, but it's how it's gotta be. All right, so there's that. All right, another important formula we're gonna want for MCDE, that's your net recombination rate. So that's R net is equal to your excess carriers, so your change in P or N, that changes depending on the problem, over your tau value. Your tau value could be P or N, changes depending on the problem. Now, as we just said, there were some notes we have to make on our formula sheet for later. Important piece of information about recombination.
Sorry.
We know that if recombination is equal to 0, or we're told by a question that recombination, let's go back one. If we're told by a question that recombination is equal to 0, like right here, assume there's no recombination inside the semiconductor, that actually causes a term to drop out of our total MCDE equation. So we'll detail that when we draw the MCDE, or write down the proper MCDE formula. So now, since we're talking about it, we're going to write down like the full non-simplified general MCDE formula. No solutions for it yet. So the full formula is, the partials with respect to your change in the carrier with respect to time on the numerator, d of whatever value. So I always default to n, d squared, change in n over dx squared minus change in n over tau n plus GL. There's that. Now, we have two general solutions that everyone should be familiar with because he's detailed them heavily by now. And then we're going to go over the two other special solutions we know of. So the general solution when there's no spatial derivative is the change in your carrier. I default to n. So change in n with respect to time is going to be equal to a times e to the negative t over tau, I default to n plus GL tau n. And that formula has a further simplification, but only in certain circumstances. So it's not one to just have written down generally, because that depends on the circumstance of the problem. So we're going to forego it for now. Then when there's no temporal derivative, or when it's spatially dependent, we do change in n with respect to x now is equal to ae negative x over lp, or ln since we're ln here, plus be to the x over ln plus gl tau n. Now, just one general note, since we've been writing GL a lot in these questions, if you're in a dark condition at any point in a question, know that your final solution will no longer have GL tau n in it, because the GL drops to 0 under the dark. All right. And since we're at this point, you can make a side note to value your ln or your lp is equal to the square root of dn times tau n. For because that's going to need to be plugged in for certain solution sets. All right.
I know you went over this already, but why? I'm just confused on the square root with the LP.
Yeah. Okay. So when it comes to the simplification, so let's just have 0 is equal to dn with the recombination rate. Let's just forego light. Light's not there this time, so it's in the dark. When you divide dn across all terms, divide 0 by dn, nothing happens. Divide your central term by dn, the dn drops out. It's just a central term. Divide, you divide the change in n over tau n by dn, and that's going to become change in n divided by dn times tau n, because that's just how division works. If you divide 1/2 by 2, it's 1 over 2 times 2, which is 1/4. That's just fraction stuff there. Right. Now, what we know is that ln is equal to the square root of dn times tau n. Well, we're looking at this and we see that our denominator is dn times tau n. So what do you do to get ln equal to dn times tau n? You square both sides. Square ln, square that. Now you have ln squared is equal to dn tau n. And that's how you replace the denominator of the recombination portion.
Oh, you replace it with ln squared. Okay.
Yep.
That's why it's squared. Okay.
That's it. That's the full thing. I didn't know that in the test on the quiz, and I just barely like algebraited it out right
Oh,
before.
really? Yeah. See, I got that one wrong.
I freaked out. I was like, oh no, how is this not on my formula sheet?
I just left it as dp whatever,
Yeah.
and it was wrong. Apparently, I don't know why that's wrong, but okay.
Yeah, I know. I guess there's just some reasoning behind the simplification. I guess I understand because like we need that diffusion length because the diffusion length appears in the final solutions.
Yeah.
So it's for some reason we got to get it somewhere, and that's just how.
I also got the J stuff wrong because I didn't freaking take the derivative. I just plugged in the 1 micrometer into.
You bet your ass I got those wrong.
Yeah. And I wasn't sure on the signs either.
I knew the signs. It was negative, positive. There was some
reason. Was it
reason,
just based on the derivative?
I remember I didn't do the derivatives right. I got that wrong. But
yeah.
All I remember is whatever I did produced the correct signs. And I knew in my head at the time that I was 100% right, but I completely forget why now. I just know I was right.
One other thing, I asked them if we should ever use negative for Q, negative 1.6 times 10 to the whatever. He said always use positive. So.
Yeah. Always use a positive there because that's just well, because Q is the charge of an electron, which is like generally negative, but the charge of a proton is just the positive of that. Charge is the same between those particles, but mass obviously isn't. But the reason we're using positive probably has something to do with some type of referencing that we decided to
I just know on his formula page, he has it as negative, so
he's not wrong.
Tricky.
Yeah, but I can definitely see why, because then if it was negative, then it would just like, it's definitely just accounted for. Because like the trick is we're taught, like we're not taught how like certain graphical representations are like come into existence. We're simply just, we're taught that they are this way and this is how you use them. Like there's a lot that needs to be said for like the fact that like the graphs didn't just exist before humans. Like we created those too, and those systems have their limitations in representing information, but they also have advantages. And I would say that the reasoning behind us using positive has something to do with the fact that like our graphical representations of like energy band diagrams and that type of stuff are already like referenced to just an absolute value of term, or they're referenced to EI or something. Because like if we used negative in all points there, it would actually invert the Fermi level. Like there's a bunch of things. Either way, we'll take his word on it. I don't know the actual reason. I'm just speculating. There's probably a pretty good explanation on some physics site somewhere. All right, we went over the general solution cases for spatial derivative absence and temporal derivative absence. Now we need to go over the special cases that we discussed earlier. The absence of a spatial derivative, the absence of a temporal derivative, and the absence of recombination rate, and we'll just leave light in this time because that's you'll know that. So what we'd write for that, so in the absence of in the absence of temporal and recombination rate, which is the example we worked in this practice midterm, the formula is a x plus b plus GL tau n. Now remember that GL tau n might not exist depending if light is on or not. So that's up to your discretion if you read the problem.
Can you repeat that real quick?
Yeah. Change in n with respect to x is equal to ax plus b plus GL tau n.
And the tau is going to be the minority.
Yeah. So when it comes to writing formulas, I default to n every time so I don't confuse myself.
Yeah.
Because if you mix and match them, then you might actually be like, oh, well, it has to be them. But no, if you always default to one or the other, then you should be you should know what's up. So there's that one. So that's a special case for no temporal derivative and no recombination rate. And now we're going to do the special case for no spatial and no recombination rate. So that is, as Andrew said, is the change in n with respect to t now. Change in n with respect to t is equal to, wasn't it just straight up a?
No, if
What was it?
if the recombination rate is still in there, it's
No,
AT
no, no.
plus B. Oh, wait,
Yeah,
what?
yeah, no, I wanted the one without the recombination rate.
He said that it was just equal A, but he said he wouldn't do that.
Fine, we'll just do AT then.
Yeah.
Wait, how do you get to the AT plus B though? I don't remember having that one.
Wait. You said if we have time and the recombination rate, it's AT plus B?
Yeah.
Isn't no spatial derivative? That's the only thing dropping out. Isn't that our general formula we know already? Just the AE? Yeah, it would have to be, right? That's the only. Yeah, there's got to be some type of like communication error there between you and him.
Yeah.
Wouldn't it not be that though? Because isn't the general for no spatial AE to the negative T over tau plus GL tau?
That's what we're saying.
Yeah, that's what we're saying. Yeah, it should be that.
Oh,
So,
you're just wording it differently.
Yeah. So
it's the same thing.
So this last case that Andrew's saying that we probably won't use is I think what the proper solution would be, because I'm thinking about it and it's right. So it should be if you have no spatial and you have no recombination rate, your answer, you would just have the partial n with partial t. You take the the derivative of that or whatever. Wait, derivative or integral? It's the integral, right?
I don't know how to find the general solution.
Yeah, cringe. I don't know what we're doing. It's just equal to a.
Yeah,
but he
I
said
have
we're
no
not.
clue. I just
He said we're
memorized
not.
that they're
Yeah,
equal.
he said we're
That's
not
that.
going to use it, so it doesn't matter. But just put down like nt is equal to a for no spatial or recombination rate.
For nothing.
Yeah, basically nothing. No spatial, no temporal, no temporal
No, okay, I remember.
recom. What do you got?
No. So if if the space drops out and we're left with time and recombination rate,
Yes.
that's when you have A e to the T over tau P plus TP
Makes
GL.
sense.
But if you don't have space or recombination, then it's just AT plus B.
Gotcha. Makes sense.
Yep.
All right, we can write that down, but it probably won't come up as he said.
I just wrote that if there's no recombination, then it's going to be A times T or X plus B.
Cool. I have my 4 down for that. All right, let's check one more time, read through all the formulas, see if we missed anything important. I see no problems. The last thing we need is a trick formula just in case for homework 1. Oh, wait, no, let's get resistivities down. That's probably something important that we should have. All right, hopefully you guys still have space. Resistivities are definitely valuable. Yeah, we have all that down. We didn't put resistivity down because of our infinite wisdom. Cool. So there are various simplifications that you can do for resistivity formulas, but I'm just gonna have us write down the general, because if you know, because the general works fine as long as you just know how to add like small and large exponents. So
I agree with that.
yeah, so the general resistivity formula is rho is equal to 1 over I'm gonna slightly modify the general, is equal to Q times the quantity mu n times n plus mu p times p. Normally, in most questions we've had that revolves around this, he's always made the mu values equal to each other. In that instance, the further simplification is going to be q mu times n plus p, all under 1. But in this instance, I'm not going to assume that's always the case, and I'm going to only take out the q, because that's always a constant. So that doesn't need to be distributed. So there's that.
I'm curious, what's the trick formula for homework 1 though?
Oh, the trick formula? Yeah, I got you. It's the quadratic solve for when they're approximately similar. Because the discrepancy in how many areas
at time equals 600.
Oh no. Here. It's a bit it's annoying, because the reasoning behind this thing's existence is because the law of mass action is an approximate solution that doesn't hold Oh yeah, here. So I was talking all about how the law of mass action holds everywhere for equilibrium silicon. That is incorrect. There's one case that I talked about earlier. So what happens is if you're working with, let's say, ND times 10 to the 11th, the law of mass action is not going to hold for silicon doped at that level, because in order for the law of mass action to hold, the amount of holes and electrons have to be at minimum 10 to the third, like 10 to the third apart from each other. They have to be in order of 3 orders of magnitude apart from each other. If they're 3 orders of magnitude apart or more, law of mass action good. If they are 3 orders of magnitude or less apart from each other, it becomes, significant values that can like actually change your answer. So you have to use the specific quadratic formula version. So you can write down the fact that it's only useful in that specific scenario down next to the formula once I get it for you. We're going to treat this, as I said, we're always going to treat this with respect to n. But if you want to solve for the opposite, you simply replace n0 and nds with nas and p0s. So here is the quadratic formula for approximate solutions when they are less than 3 orders of magnitude apart from each other for equilibrium silicon. Note that this formula is, I'm pretty sure, only valuable for question 1s, like homework 1-2 things. Anything else, we're going to use mass action. Or potentially Pn junction. He could make us use this at the Pn junction. I doubt it, but he could. So just keep aware of it.
I'm sure that this formula works regardless.
It does. This is like the super specific, but we don't need to do it unless.
Yeah.
Yeah. So, because like the same way the quadratic formula always works. Like,
yeah.
But why do that when I can factor it? So the formula is ND plus the square root of ND squared plus 4NI squared. And I'm pretty sure it's the NI squared, not the quantity 4NI squared. Remember that. So use parentheses if you must. Then that's all over 2. And that's it. And I'm pretty sure that's everything we need to know in terms of formulas. So, I mean, you could write down like charge neutrality, but that's just like basic addition stuff that you really won't need to know. That's more of an intrinsic piece of theory knowledge than it is a formula, as far as I.
Which one is that?
That's like I don't remember it. I put my notes away. It's basically, I don't know the formula itself, but I just know that it's basically stating that for every free electron you generate a hole with it that leaves the charge. It basically says that for equilibrium silicon, the overall charge on the silicon remains neutral regardless of the amount of carriers generated by doping. Or for that matter, regardless of the amount of carriers generated by a higher temperature once it's at the steady state of generation. If you you turn it up to a certain temperature and leave it for a long time, then it would still hold. That'd be cool to see temperature variation as something I would have to contend with, because in real life, it's very obvious that there's probably a more complex formula that models it more properly, because if you think about it, like a CPU it changes temperature pretty quickly and constantly, because of the nature of its use. So I would say that there's probably a more complex formula we haven't been taught yet that deals with that specifically notes it's not just space and time in a semiconductor that matters. It's also a varying temperature that has varying effects on all these different values, because we've been taught all these temperature effects, but we haven't been it hasn't been detailed yet. Either way, that's not something you need to actually know, so at least for our purposes. So that's cool. Anyone have further questions or stuff that they'd like to touch on?
I just want to double check that I have all the resistivity formulas down. Can you repeat which of those are which?
So for resistivity, we're just using one formula. There are a bunch of resistivity formulas, yes, but as far as it goes, the formula is used across the board, everywhere the same, and as long as you know what values to plug in, you can use the general formula to solve for everything.
Okay.
So the general resistivity formula, I'm going to say it without my simplification, just so you get it absolutely correct. So it is rho is equal to 1 over Q times mu n times n plus Q times mu p times p. Now, for our purposes in his questions, most commonly the mu values are the same and q is a constant, obviously. So the further simplification for this formula is rho is equal to 1 over q times mu times the quantity n plus p. That is probably the formula we'll need to use, but the general formula is the best one to have down just in case.
Okay, so for the one that he uses in question 1, is that just this split off because the other part goes to 0?
Which question 1?
So in the question 1 on the review slides, for part C, is rho equals 1 over q mu n nd for doped
review
silicon.
Slides. Which review slides we talking
The PowerPoint one
about?
for lecture 12.
I think I can
page
just open.
4.
I'm pretty sure the PDF is the same, so I'm gonna open that one instead because it's quicker. You said question 1, page 4, right?
Yeah.
Gotcha. All right.
Part C.
All right. So here's the. All right.
That's just because it's canceling out, right?
What's canceling?
Are you asking me why there's a difference?
Yeah. So like
between these numbers,
instead of it being 1 over that, right, for the resistivity, it looks like he split the formula into 2 parts, right? So I'm assuming that the other portion of it went to 0 because you have the 1 over q.
No. He didn't do that. He didn't do that. So
Okay.
You can see that here, or at least in this question, mu n and mu p are equal to 100 and q is equal to q. So the first thing you note is he does what I do, which is always pull q out. He doesn't leave it distributed. Right. And then he multiplies it by the quantity 100 times 10 to the 18th plus 100 times 100. Here's the trick. This obeys the law of mass action. Therefore, p is equal to 100 here, or 10 to the 2nd. Our mu's are equal to 100, so it's a little deceptive that you thought a piece dropped out when it was actually simply that the p was smaller than we're used to using. He could have written as 10 to the 2nd to be more obvious.
Okay.
So he still used the formula like it's meant to be used. You can see that there's 2 100s on that side. So it just so happened that p was equal to the mu value. So it looks a little different.
Okay.
Yeah, and then on the one below it, it's simply a different case where he's using intrinsic silicon, which, by the way, intrinsic silicon, the formula simply becomes, I did that wrong the time I did it earlier. I only used one. I only used, it's Ni squared for this one. So the formula for intrinsic silicon is the same formula, but instead of putting like 10 to the 18th, you put in 10 to the 10th for both n and p. So I remember that. So I messed up that earlier. So I was off by a couple orders of magnitude.
Right. Okay.
Yeah. So in that instance, you could also say for that one, for intrinsic silicon, you could say it's 1 times 1.6, whatever, like times q, like 1 over q times your mu value. Let's say the mu values are the same. Let's say, so it's 1 over q times mu times 10 to the 20th. That's what that would be for intrinsic silicon. Wait, no, it wouldn't. Shit, I'm just monkeying myself, aren't I? It's plus. No, I was right. Never mind. My question was right. Never mind. Ignore me. I explained it correctly the first time. I got the right number. I'm just rooting myself. All right. So any further questions beyond this stuff, besides the resistivity?
Do you think you could DM me a picture of your formula sheet? I had to go in and out a couple
times. Yeah.
I can.
I'll just take a picture of the formula sheet and send it to General. It doesn't need to be DM'd. And formula sheets aren't cheating as long as they are formula sheets. So you're fine to just share them amongst students. There's no rule against making them collaboratively.
Yeah, I had to go let out a dog a couple times.
All right, I will take a picture of that now for you.
Thank you.
Let me make sure that this is a good picture. I say that's
how big did he say our formula sheets could be?
I think he said one side of a piece of paper.
What's the size?
I've been using one size of an average size piece of paper, and I think you're only allowed one side. And I've been using it for both tests so far, and I make it a point to show the respondus camera my formula sheet in full, both sides. So I haven't been docked points or called to the Office of Academic Integrity or anything. So I don't think it's cheating. I think my way is fine.
Yeah, I've done the same thing too.
Yeah, so we should be good on that. That should be no problem. So I'm pretty sure that's detailed somewhere. I just don't remember where. So there's that. Any further questions or anything? Because other than that, I will stop the Zoom call and upload this to YouTube. If you guys want to rewatch it or ask questions to me again in like DMs or general chat, I can answer them. But I do have a digital logic lab. I believe I have to go do now.
Ooh, nice. That's a fun lab.
It's lab 3. It probably is fun. I enjoy using the Quartus software and I enjoy the DE10 Lite very much. I use it for personal projects now because all my Arduinos are locked up in Alabama. RIP.
Right.
So it's cool. I like FPGA. Personally, I understand why FPGA is the shit, but I still like microcontrollers better at the moment.
Gotcha.
That's just how
Yeah,
it is.
just don't forget you only have 15 minutes to upload your work after your midterm's over.
Yeah,
Yes.
that's definitely an important
That would
note.
be a mega oof.
Yeah, so
Yeah.
what I tend to do, because I've had to do like work upload midterms this entire, session or this entire like semester. So the trick that I do for it is I have my phone in my phone beforehand. I prepare it so the moment I unlock my phone, it opens to like, Office Lens or whatever. And then the moment that starts, I immediately open Lens and I just immediately take pictures. So what I do to even speed it up even faster is when I'm using the notebook, I only use the right side of the notebook for each page. So I'm wasting paper there, yes, but at the end of the day, what it allows me to do is just flip pages and not have to readjust my camera angle. I can hold my phone stationary and just keep taking pictures because it's all on the same side, so it ends up in the frame every time, just for speed consideration, because I had problems with it last semester during finals for my physics 3 exam. Like
Yes.
she was Kelsey was understanding about it and everything.
Yeah, because Kelsey's the best.
Yeah, because it was the first time. But at the same time, like it was ruining me because at the time I didn't have Office Lens. I was using some other like third-party Garbo PDF scanner that was like not working. And it took me like half an hour to get that done. And it's good that she's understanding because otherwise I would have been accused of like augmenting my answers or something.
Yeah.
So how is that better than like the Notes app on like the iPhone for like a PDF?
What's the Notes app? I have an iPhone.
Well,
What is
just
this? What is this wizardry you speak of?
Yeah, the Notes app on the iPhone is a built-in PDF scanner.
Are you kidding me?
Yeah.
I'm not. That's what I do. I literally scan it on the Notes app and then email it to a separate email, and then that's how